if I can do it. Okay.
Okay, so we'll start in 2 minutes.
In 2 minutes, okay. Yeah, I can also start my timer here, and you say restart.
Here's the plus. And that sounds.
Oh, okay. Oh, you're projecting it, okay, on the screen, obviously, yeah.
Oops. I lost my screen. You can still hear me, right?
Yeah, I hear you fine.
Monitor.
Okay, I can.
Okay. I'm gonna mute here so that there is no echo. So you probably don't hear my introduction.
So today we have the pleasure of having Dr. Ali Rosser, joining us in Vancouver. He works for HCR, and we're going to talk about the seismic evaluation of dams and navigation structures using Finite organizers. And if you want to questions that you can have, and so Ali, please go ahead.
Hi everyone. Hopefully it's the right time to start and you are hearing me clearly. My name is Ali Rasek. I'm a senior hydraulic structures engineer with HDR, and your Professor Malek, he asked me to just present to you guys some of my experience with FEA analysis, especially for hydraulic structures. And hopefully I can cover a couple of old projects for you guys here today to just encourage you to follow this line of work in a way and career. Firstly, I try to rather quickly present a work that I did maybe about 15 years ago on Panama Canal third set of locks project. And my second presentation, which I quickly put together today, is about a dam project that I did more than 10 years ago. I'm using the two old examples, but this line of work continues and is becoming slightly more popular as well. So there are more and more opportunities for this type of work recently. The expansion of Panama Canal, this is a plan that the government of Panama had about 15 years or maybe about 20 years ago. They started thinking about it about, say, 2005. The Panama Canal was built more than 100 years ago, about 1915. And It consists of, hopefully I can use my pointer here and you guys can see it. It basically what we call, big picture, we call it Panama Canal, but what it really is a bunch of canals that connect the two oceans to each other. The Pacific Ocean and the Atlantic Ocean, they are connected to each other using Panama Canal. So it's canals and a man-made reservoir or lake and a few lock systems. And it was built like that and it continues to act like that. The picture is slightly counterintuitive, like if you see, look at the key map here in a way, because the continent rotates at that point. Therefore, Pacific is on the right side of this map and Atlantic is on the left side. And basically, so there's this canal systems and there is a change of elevation between the ocean and the lake in the middle. And therefore, we need the lock system basically to lift up the ships and pull them down. And when I explain a few more slides, it will become more clear to you guys. However, big picture is that there's a lock system on the Atlantic side, as is shown in more detail here. There are locks which have been functioning for more than 100 years, and these are the locks that we designed, and basically it's probably functional. And so again, this picture, this small portion of the picture shows the comparison of the older system and the new system, which was built. Comparison in size, the older system is smaller for smaller ships. There was a standard size that could go through the Panama Canal because of the locks. And the newer locks, they can accommodate larger ships. And also the water system was kind of innovative to reduce the waste of fresh water because this lake in between, it uses fresh water basically. And similarly on the Pacific side, there's another lock system. So the ships go up into this freshwater lake and then go down back to the ocean. And this is the city of Panama City, which is by Pacific Ocean. Again, counterintuitive, Pacific Ocean is on the right side. And a close-up of the new lock system versus the old lock system. And as you see, the old lock system was two-way, and then the new lock system is single-way. So at one time, one ship goes down, and then maybe they stop, and then another ship goes up. So it can function in both directions, but one at a time. So, but it's bigger, and it uses this water system to save water, waste of water. And here I indicated 26 meters elevation difference. That's where these lock systems help with basically pulling the ships up or bringing them back down to the ocean level. Again, another picture on the sizes. The new one is bigger than the original lock system. And this picture, I cannot remember whether it's rendering or it was taken, I think it was taken after construction. So this is post-construction where the new lock system is functioning and the basin system is also functioning, which reduces the waste of water. And I will show another slide that make this more clear. Now here, the water saving basin, how those 3x3 water saving basins help with reduction of waste of water and how the water goes from basically how the lock system is filled by the water that is saved in those basins. and then it's reused, and only 40% of it is wasted. It was a design build project, so we were hired by the contractors, and I have written the name of the contractors there. And I was working with Tetra Tech at that time, which was one of the companies which was working on the structural design or general design. So this is high performance and efficient operation and maintenance, and reduction of consumption of fresh water, which is a big issue there because that reservoir is basically the source of fresh water for the country of Panama. And estimates of the cost. Yeah, I can't remember whether it was the real cost or the previous estimate. Maybe it was the total because I have noted down the completion date. This picture is rendering, and it shows the log chambers, 3 log chambers. So the ships go up in 3 steps, at least 3 steps. And again, the water saving basins, which helped with reduction of water waste. Log chambers are there. So structurally, like what was important to a structural engineer was the design of the log chambers where the ships stay at every lift. Wing walls, these are like this end, like they open the wing. And the approach structure, that's maybe terminology from ship industry, where the ships come close and they may hit this structure and until they are positioned to go into the canal. And this is obviously a rendering. And this is our design team about 15 years ago. And new lock system under construction here versus the operating lock system. However, nowadays this is completely functional and is used by the ships. So getting into the seismic structural portion, we always discuss the response spectra that is used for the design, like the hazard. Maybe sometimes we call it hazard, and the hazard on the 2 sides were substantially different. So one side is the Pacific side, and the other side is the Atlantic side. They were at that location, which is probably the narrowest location on the continent. They are distanced about 100 kilometers. And however, still the Pacific side is much more active than the Atlantic side, although it's only 100 kilometers apart. And this is the hazard for like higher probability earthquake that happens average 1 every 475 year, the lower one, and the lower probability one that happens 1 time every 1,000 year, which has a higher value. And the analysis design was done in 2 levels. Different criteria for each level of earthquake, but both levels were considered. And we used the acceleration time history analysis and solution for evaluating the seismic response on both sides. This is the list of the earthquakes that we used for the analysis and design. And they were chosen based on magnitude, a style of faulting, distance to rupture, and site characterization. I mean, similar to what is customary to be done, and geologists or geotechnical engineers, they are normally in charge of finding the best fit earthquakes for that design. And we normally go through a process that we call earthquake deconvolution. And the reason is that the geologist normally gives us earthquake at the surface. However, our models receive earthquake, or we apply earthquake to our models at the base of the model. And this is like a backward question, like what was the earthquake at the base which caused the earthquake at the surface? And because there is some damping in the system and other issues, the earthquake at the base should have been slightly stronger normally, or maybe slightly different than the surface to cause those motions at the surface. So this is a process. There are different methods for that, and it's slightly more important for softer materials or rocks, less important for really hard rock. That's like very minute for hard rock. But we go through that to make sure that we are applying the proper earthquake at the base of the system that you will see. Typical monolith sections, like order of 3 meters high. This is the log system. So that's just, I picked, or actually I did this presentation first time many years ago. So at that time I picked a typical log system section just to show what we are talking about in terms of dimensions. Order of 30 meters in elevation and about 30 meters in weight. And there is a complex water system going through the logs, which basically connects the chambers to those water basins that I mentioned. This was a sophisticated system. It's not only filling and emptying, because only filling and emptying waste a lot of water. And they designed a complex water system which saves basically 2/3 of the water, or reduces the water use by a factor of 2/3. If I'm right, yeah, 60% reduction. That's those pictures that I showed you, about 60% reduction in use. For us, structural engineers, or we did like a structural and foundation interaction analysis. This is a typical model that we create. Okay, sorry, page up, page up. Okay, this is the typical model that we create and finite element mesh. So remote rock, and then this area is closer by rock, which we use finer mesh and maybe more sophisticated material model. I cannot exactly remember, but maybe we used nonlinear model or maybe we didn't. And then interfaces with the structure. This dark one is a typical lock that I showed in the previous slide. So that's embedded in the model. Representation of the water, like compressible water model. There are different solutions for that. We use one of the typical solutions, which I remember was using a acoustic representation, but there are different solutions for that. And some rock fill or earth fill behind the each log to fill up this gap, which we use for this one. We use nonlinear material model. Because I previously presented this for a class like yourself, FEA, I also showed off something that is familiar to FEA students, like the different element types that was used in there. So this is a better close-up rock, a linear rock, close rock, which might have been nonlinear. 2 levels of backfill, 1 level saturated, full of water, the other level, no water. The structure which we are designing and the representation of the water. Remote boundary conditions are important for us, and we always use in one type of solution, or which is more correct, more physically correct, and I may get to explain that in the next deck of slides. The more correct, physically correct solution, we use massed foundation, which we used here, and then to accommodate movement of waves, we should use absorbing boundary conditions at the remote boundary so that the waves, the like seismic waves, can enter the system and they can leave the system and they are not basically trapped inside. Otherwise, we will get unrealistic results. And these absorbing boundaries, they are basically dampers and they allow the exit of the waves. And we use frictional interfaces a lot. Maybe I explained it here that some of these interfaces are tied and some are frictional. Like water, rock to slab, this is tied because we really tied this down by devils, so we didn't want it to jump up. And then everything else is frictional, and we got the parameters for frictional interface from the geotechnical engineer. Devils tie down the slab. Yeah, I noted down here because it was devil down. So, I mean, initially we didn't use frictional in the model. It was flying up, obviously another proof that they need to be devil down. So in the spec, we changed it to devil down, and then in the analysis, tie them down. Explanation of material properties. We always like present them in presentations and reports, etc., based on what we receive from lab tests or excavations and boring for geotechnical models. And we applied hydrostatic water pressure directly for sometimes we do it directly. So depending on, again, mentioned a strategy for basically what a strategy used to account for water. Sometimes the way I like to do at that during that project was to use acoustic model for water, which couldn't take weight, but it could apply the seismic pressure and at the same time apply the hydrostatic pressure directly at the interfaces. But there are different strategies for that, but we shouldn't remember, we shouldn't forget actually either one. Both the hydrostatic effects and the dynamic effects should be accounted for. Yeah, we use the frequency sweep to get the primary period of logs. Normally, you can also do modal analysis, but most software would do modal analysis for you. However, sometimes the system is too complex, or maybe you don't want to remove the nonlinearities from the system and just want to use the system as it is and estimate the primary modes of vibration. Then you do frequency sweep, which means you redo the analysis with waves of various frequency, and then you will see which frequency results in the largest response, and that's the primary frequency of the system and correlates to a primary period of the system. So that's what we did, and we estimated the primary frequency or period. This is period for horizontal and vertical. And the range of interest is normally important to us because a lot of parameters are set to the range of interest. And yeah, sometimes for dams, I use say 0.5 TN to 1.5 TN. Or yeah, I mean, depends on the structure, but it's engineering judgment. So say in this case, 20% to 1.5 times. That's the. Oh, you have a question?
Yeah, I have a question.
I'm getting. Is there something in chat?
Okay, let's split it image.
Okay, over here. Do you do any model analysis? Yes, yeah, especially for dams, we start with a model analysis. It's a good test to see, to check the periods and also make sure the connectivities are there and model. That's like our first test model to make sure everything is working. But as I said, when the model is complex and nonlinear, and you don't want to like like for this project, say a trivial strategy is to just change every connection to tide and make the model linear and then run the model analysis, which is a linear process. However, sometimes you want to just check the system as it is, and therefore you just do the frequency sweep that I mentioned, just excite the system with a bunch of different frequencies, just in simple words, or actually practically that's exactly what you do. Just apply like a bunch of frequencies, like maybe you can by book or by experience, you know that the frequency or period would be about 0.2, and then you excite the system by periods between 0.1 and 0.3. And then you will see that at 0.22, you see the maximum response. And therefore, you conclude that that's the primary mode of vibration. Okay. And then damping parameters, again, we set them at the frequency range of interest. And that's used to be the most famous or popular parameters that we use to describe the damping are still very valid. It's called the Rayleigh damping. And at that point, we just found the parameters for Rayleigh damping. System damping is important because every system damps energy. And if you don't properly account for that, then you get basically overexcitation. And this is the typical stress output. Just I have put in typical responses. Another question. Can you go? Oh, sure. Yeah, sorry. Okay, yeah, probably this is more visible even for me. I couldn't read it. So different stresses to look at and conclude about the structural safety in a way. Like probably the 2 was vertical, so the vertical direction stresses, maximum positive numbers probably show tension. This is Abacus software. Every 2 software are different, but as I recollect, Abacus was the same. So positive is tension, negative is compression, and you go by your structural design book to check if this structure is safe. And however, I should emphasize and remind myself that this is a reinforced structure. So you just really go by section design and check sections for section forces rather than localized stresses like your beam and columns in the structure. But the programs and Abacus is the same. They allow for output of section forces. And then you can use your Canadian or US standard or international standard for design of the concrete sections. And the other side, I showed the reactions on the rock. And again, rock has a capacity, and you check the maximum compression on rock to make sure it doesn't go beyond the limit. And we check the displacement of as well. Like that is the earthquake that probably caused the highest level of movements. And there is a seismic design criteria. So something specific to this project was that it had 2 levels design criteria. One for more frequent earthquakes happening like average one every 500 years. And another one for stronger earthquakes that happen once every 1,000 years. For more frequent earthquake, no permanent damage, and just continue with operation as if nothing happened. And the mechanical components also continue functioning as if nothing has happened. And basically, yeah, in summary, as if nothing happened, just continue functioning. For higher criteria and higher earthquakes that happen less often and less frequently, but they are stronger, as I previously shown, basically we don't want anything to collapse. Like there might be some damage, and depends on the project. For this particular project, it was assumed that they can do some repair, but they don't want any major safety issues. So they set limits on maximum deflections in the whole system or in the walls, and limits on the displacements. That's a two-level design, or sometimes it's almost what more recently we call it performance-based design. So different performances for different demands, basically. And again, another picture of the wing walls that we were in charge of design of the wing walls as well. As I said, this continuation was the log system. Just for you guys to know the scale of the wing walls, that's where the ships arrive or exit. And we also created 3D models because especially the wing walls, they were functioning very 3D, like they are 3D shapes, obviously by shape. At that time, 15 years ago, our computer systems were not as advanced as they are now, or maybe even not even as good as 10 years ago. We didn't have access to cloud system. So we were trying to save a number of nodes and elements. So based on my today's standard, these are poor quality meshes. We could do a lot better, but we really studied, like, is 2 elements good enough? If 2 elements can give you a good estimate of bending, then don't do more than 2 elements. Like at that point, or maybe even before that, a lot of energy was spent on just putting the minimum number of elements or nodes that can capture a good estimate of the response. But nowadays with cloud computing, etc., we can be just generous, and some people are over generous. They put so many elements on everything that, again, it could not be finished in a matter of days. So, but at that time, yeah, we just wanted to use a 8 processor laptop or computer, which we bought the most expensive one, but anyways, a limited number of processors on a single system to just have a good estimate, the best estimate that we could get of the performance. We also took advantage of, in a way, subsystems and submodels. We run some of the analysis 2 times. One, like the big picture, bigger model, to get a history of reactions, and then apply those history of the reactions on a smaller model, which was like, this model was intended for, say, this structural member. The ones that are far away and they are irrelevant, they have poor mesh, but the one that we were designing, it has a finer mesh. So we were also using the like 2-step analysis because there was no easily accessible cloud computing at that time. And yeah, so when you get to that member or a structural member that it was being designed, it was more properly meshed with a better quality mesh that we could afford at that time. And we were reading the structural response because it was, as I said, it's a reinforced structure. So it's basically element response was less relevant, and a structural section response was important for our design. And we always discuss the load combinations. That's what we use for the particular present, and structural engineers are familiar with that discussion. Design criteria again. So we explain the criteria being more difficult for the more frequent earthquake, in a way more stringent for level 1. That is in terms of the design to capacity ratio, what it meant. So that was more detailed for the design basis. And the less stringent for the less frequent earthquake, and allowing for a little bit of damage, which is like might stop functioning of the system, but it's not a safety issue. Just some details of the interactions. We try to make these steps also automatic so that the program or the Abacus program, FEA program, creates the demand, and we compare with the capacity per the interaction curves of concrete books, and make a decision about the design, whether we should make it thicker, or a lot of times dimensions are set, and you should add basically to the reinforcement because it's a reinforced structure, luckily. And yeah, because I already burned about 35 minutes, this was another study that I did related to Panama Canal, but I don't go through this. Instead, I jump onto a dam project for about 10 minutes. This is one, okay. Let me set it to full screen. Yeah, this is one of the very first dam analysis projects that I did more than 10 years ago. And I was always very proud of this study that I performed at that time, about 2014. And basically the whole learning process, it was a tight deadline. So the whole learning process and using the software, because we were using, or at that time I learned that the owners, a lot of dam owners are in the West Coast. They are interested in Elestina software, and we learned it and we used it appropriately in a very short time, like within 6 months, learning and implementing and producing the results, which was pretty tight. However, after this finish, I was very happy, and I went on a longer vacation, and I almost never presented this. And so I was thinking, oh, I need an opportunity to put together a presentation for this. And maybe this morning I had time to, after more than 10 years, to pull out some plots, etc., and present it to you guys as one of my older projects. But but then this is work in progress. So the previous slideshow, I have shown it maybe 4 or 5 times, and it was improved through time, but this is the first time, and I just wanted to have something to show to you. Luckily, because I was disconnected from this project for more than 10 years, I found out maybe a few months ago or last year that because this project is archived, everything is available in this website. This was a study of a dam which was never built, and basically the owner archived everything. So everything that I showed to you, which was my work, is accessible through this website, and you can go to this address, basically go to documents, and there is 1,000 documents there, and some of them are related to earthquake analysis. And again, pulled out quickly from the website. This dam was going to be built in the state of Alaska in the US. And I mean, big picture is close to Anchorage, but probably a few hundred kilometers, not too close. And so basically the idea was to build to energy generation. They wanted to generate energy. That was the top reason to build this dam, so that it should be a source of green energy for the state of Alaska. I don't think they needed water in the vicinity, or maybe they needed a little bit of water as well, but this was mostly for electric energy, just making electric energy or producing electric energy. And yeah, so this is the schematics of basically river going to the Cook Inlet, maybe Cook Inlet. Like these distances are not real, so this is far away, and they wanted to produce energy there and then transfer it to throughout the state. And yeah, again, I don't know if this picture is helpful or not, but this is like the location of the dam, and probably the city of Anchorage is at a distance to it. And schematics of the dam. This was, again, I don't know if the previous one had the dimensions as well. Okay, size is also the height. The height is 700 feet, order of 700 feet, which is over 200 meters. So for us structural civil people, we are interested in the sizes. And yeah, so that was going to be a relatively tall dam, was planned to be a relatively tall dam, and but it's not completely arc dams. Like this is arc shape, but it also has a lot of weight. So we may call this arc gravity, like it uses both the weight and also the arc shape to withstand the water and then build up a huge reservoir here. Water would be transferred to a water generating, electricity generating a station, and then electricity is produced, goes to substation, and goes to the grid, in summary. Geometric rendering that we prepared, and I probably forgot to mention that at that time I was working with the company MWH, which was world famous for basically dam design in a way. Again, H was standing for Harza, and Harza, if you look at history of building dams, Harza was a very important dam building company, or that, no, designing, sorry, I shouldn't say building, designing company in Chicago, and then it became part of MWH. And later on, the company, the Canadian company, Stantec, purchased the company. So now, like, we can in a way say that this dam was designed by a predecessor to the Stantec company. And this is the AutoCAD rendering of the dam. As I said, this is not as smooth as the previous presentation. I just spent maybe 1 hour to find these things in those reports and copy and paste. That's the model of the dam and reservoir that I created in 2014. So there's a dam, water representation, or reservoir representation. On one side, we sometimes emphasize that this is compressible because sometimes we use only added mass to, in a way, represent the seismic response of water. And a good, nice, large representation of foundation. Much better mesh here, much more presentable mesh here. The reason here is that for the first time I used cloud computing with, I don't know, like 64 processors, etc. So we could really run time history analysis in overnight in a way. Say 5 p.m. to 8 a.m. it was finished. And we could see the results the next day. So it was worth it to have a nice mesh. It's better presentation, better results, and even it's easier for the analysts to just create a nice fine mesh rather than thinking too much about sub-modeling and where the results are reliable or not reliable. Just put the best mesh possible. a close-up of the model with so many monoliths and foundation representation there. Some of the results that I pulled out from those reports say we studied the maximum tension during the earthquake, and these red zones is something to think about. I don't say that it's failure, it's just, okay, we are getting some overstress. What is going to happen? Is it a failure or not a failure? When you look at it through the thickness, you see that it doesn't penetrate much. So maybe in the worst earthquake possible. What are those multiple parallel layers? Oh, let's go back. Are these? Yeah, they look like colorful, nice layers. So on the dam side, hopefully, I don't know how is your perspective, but hopefully it shows that this is dam, this is foundation. This particular software likes to really make things colorful that maybe more recently I asked that be more careful with variety of colors that could be confusing, but basically, so these are monoliths like I don't know how many were there, maybe it looks like more than 20 monoliths of the dam standing side by side. And between them is what we call contraction joint, so that say in winter time they can shrink and in summertime they can expand. And we don't want any overstress to happen or tension happen in winter. Therefore, we put contraction joints between them. So the joints between monoliths is real. However, on the foundation side, that was just the way we created this model. We extruded the foundation under each monolith, and the program just used a different color for every extrusion. They are continuous. But maybe at that time, because I was working on a limited timetable, I didn't find out how to get rid of this colorfulness. So the ones on foundation, in summary, they are unreal. It's only one piece. The ones that we show on the dam, they are real. So it's like separate parts in a way. Hopefully it helped with clarification. And there is, for analysts, there is a friction. We use frictional interface or frictional contact between these parts on the dam. However, on the foundation side, this is only continuous. So continuing, there is no separation. It's like the same thing. Blue and green is the same. On the water side, accidentally water turned out to be blue. So this is mostly water. The water close to the dam, we use a different mesh techniques, and the program has just used a different color. The water is also continuous. So the only places where there is separation is between monoliths, where we use frictional contact, and at the base of monoliths, which again we use frictional contact, similar to what I in more details explained in Panama Canal. Okay, my time is almost over, so I just browse through some more pictures of the results, but I think, I don't know if, did I answer your previous question, Sardar, or yeah, it's still not clear. Okay, yeah, I tried my best. Yeah, I mean, I cannot, no one can really teach dam engineering in 45 minutes, but I did my best. And we can be more and more in conversation mode. I know that I want to finish in about 10 minutes. So while I'm showing some stuff, it's nice if you guys want to ask questions or why do they put multiple here for the dam? So as I said, you don't call them layer because they are vertical. So it's like vertical joints. And as I said, this is real, like the like on the dam, this red and this yellow, they are separate. They are two different parts, and we want to build them as such. I forgot what was the concrete technique that they were using, but whatever technique that they were using, we want them to be separate. Because like in winter, they should slightly separate from each other and don't cause tension. Foundation is fictitious. It's a feature of the software. Like it shows different color. It's not real. They're not separate. That's a good point. Yeah, as I said, this is the first time I'm presenting this, so maybe I should find a better picture if it's in those reports in that website. So this one I answered. Again, stresses, always stresses, and this is dams are obviously they are not big picture, they are not reinforced. Maybe in some cases there are some superficial reinforcement for some reason. But like putting reinforcement in these huge structures, normally I shouldn't be economical. So there should be really a strong reason to put reinforcement for some reason. And so in this case, stresses are more important. However, you should more carefully look at them, the extent of them. Do they cause failure? Like we are not looking for overstress zone, we are looking for failure modes. Like the question is obviously, does this dam fail after this earthquake? And we cannot say because some facial overstress was there, it definitely fails, or it doesn't fail. So we should more carefully look at that. That's generally what I can say for all dams. And okay, so I carefully look at the possible questions which are welcome. But I also show a comparison between two techniques that was more traditionally used in earthquake engineering, which we call massless foundation, and a technique that is becoming more and more popular with better software and better computational capacity, which we call mass foundation. This is more real or more physically correct. This was good engineering judgment. I have looked at some results with massless. I cannot say they are horribly wrong, at least in my cases, but then it's engineering judgment. This is physics. And besides, I should say that for most of our work, we do a lot of side studies because we need confidence in the results. That's something that we keep on repeating all the time. And there's always a lot of side studies and case studies to basically verify the solution. Like there are these two terms, verification and validation. And a lot of times you like mistakenly use one for other, but both are about trust in the outcome and in the results. And formally, if you want to be really correct by book, you should use verification for numerical modeling verification and validation for comparison with test, but that's not what people like. Sometimes they don't do that. So listen to them carefully. But however, we should do both. However, we should really check the solution with alternative solutions, and we should also make sure that they match the tests. It's very important in our case in civil engineering because that's the reason that I give all the time, but I don't know how people find it correct or not. But I say for iPhones, like you hear a report that an iPhone was broken and then the company realized that they should make it stronger. For dams, you cannot really use that idea that, okay, an earthquake came and the dam was broken and we learned something that's too late to learn. So you need to really be confident in what you are designing, like a lot more. But some people say it's not convincing. I think it's very convincing that we need to be like we seal our word. That's why we have the PE seal or PH seal that we say we really think that what we did was correct and was properly verified. So that's the part of verification. In that project, we compared two different types of solution by two different software. But we did it in 2D. That's one of our verifications. And while the solutions were the same order, but they were different. And as I said, my time is running out. That's why I'm looking at my watch. But in general, because we know that masked foundation solution with dampers, etc., they are better solution. So or more physically correct solution, we call them more correct. But the other solution is the same order, but overestimate, at least in this case. So let me show some of the results because I don't have time to go through every slide. For like this is ANSYS, as I remember, and this was the LS-DYNA. ANSYS was massless foundation. LS-DYNA is masked foundation. The static solution matches. They use different strategies, but the static solution matches, so that's a good verification. The dynamic solution, while they are the same order, the massless solution is overestimate. So in a way, on one side, we know which solution is better because it physically makes more sense, and we can explain why we use this better solution, but we also compare them and see that they are the same order. In terms of sliding displacements, again, the more physically sensible solution, which is masked foundation, causes like a lower estimate. So I have more confidence in the lower estimate. However, I see that they are the same order. Like it's not like one doesn't move and the other one is 10 inches. It's like 2 inches versus 1 inch comparable. But I know that this is better solution. Sorry, I had to go through this rather fast because yeah, it's like we have 5 more minutes left, and we just want to hear if there are questions before ending the session. So there are yeah, maybe you are typing already. I can wait for that. Thank you. Oh, very questions. Very good question. Very important questions, but yeah, it needs a detailed response. How do you decide which software to use? Yeah, I mean, choice of software, just if you want to choose I mean, think about the name of the software. It's a little bit, sometimes we call it, I have used this term, so sometimes we call it breeze of the season. Like, okay, all the software, there are quite a few very good software in the market, and they are verified by a lot of users. And a lot of them are like general purpose FEA. So even they are used by people in a different industry, and people think very highly about them, say ANSYS, Abacus, LS-DYNA, Flag, and whatnot. But it becomes, maybe I shouldn't use this word, but it becomes fashionable. Like the dam industry now has a special interest in LS-DYNA. And it's a strong and robust software. I believe in it, but I cannot say that there is no better software or no competitive software. Verification, we have a lot of different strategies depending on how much budget we have, but one of the best is what we call, or I call, progressive analysis. Like we analyze in different levels of complexity or with different assumptions, similar to what I tried to show to you guys very quickly, that okay, how the two solutions compare, one with engineering judgment, which is massless foundation, the other one more physically sensible, which is mass foundation. And can I explain the difference? So I compare the two and I say, okay, on one hand, the results are comparable. It's not like one order of magnitude difference, like one of them is twice the other one. On the other hand, I can explain that the mass foundation accounts much better for the wave propagation in foundation, and therefore it's a better solution. So that's part of the reasoning that we use a lot in verification. And the validation, as I said, still I see a lot of documents that use these two terms interchangeably, like quality management and IT, they always say software validation, but they mean what we call verification. So they are sometimes used interchangeably. And the follow-up question, the BCs for both the dams and canal included huge depths in. Okay, so I said, let me finish that one. Yeah, I go one by one. I think you are typing the questions that arrive from the students. And then there are some validation studies, especially the ambient vibration is the easiest one that we can really see how, by measuring ambient vibration, we can check the period of the dam, and that's almost the cheapest validation. And then we can compare the FEA model, but we can do as much as you can pay. Like you can do very expensive active vibration studies to more carefully study the modes of vibration. BCs, yeah, we used because the way we assume that the waves are coming towards the structure are from bottom up, which is generally assumption, which might not be real. Like, I mean, when you can imagine that the earthquake happens at a distance and the waves come towards the structure, it's not really bottom up. And we think by having, or physically makes sense by having a larger model, you can reduce the difference between the real modeling and the assumptions that we use. And people have done studies and have shown that there is a large enough model, like as I said, 3 times the depth of the dam going away from the dam makes an accurate enough solution. Yeah, thank you. No, I'm pretty good. I can stay as long as you guys want, but as we planned, it's end of session. So I'm waiting for more questions. I can wait 5 minutes, etc. Yeah.
Any questions? Okay. Oh, like so I was here.
Not clearly, but are you saying that it's over? Yeah, maybe you can. Yeah, okay. Yeah, I mean, I'm very happy that I got the opportunity to present to you guys. And as I said, we are HDR. I'm at the Vancouver office, and we do a lot of very good dam and hydro engineering. So hopefully you guys consider us for your future jobs or when you apply to the job market. Thanks a lot, everyone. Okay, good question. How do you consider impacts such as the one? Oh, was it a canal? Okay. I think there was something in the Suez Canal, maybe you are talking about. Yeah, as I said, that's not the whole canal that we are designing. That's only the lock system, which is a very small portion of the canal. And I think it's operated a lot more carefully than the rest of the canal. So one top answer is operation. Operation of the lock system is a lot better than operation of the lengthy canal. And besides, as I said, the lock system also has approach structure, which is designed, actually one load case was impact. So it is designed similar, like I explained to you the basically seismic design, and there is also impact design for multiple levels and different probabilities. However, I think the top issue is operation, like operation of the lock system, because it's expensive and it's super important. It's a lot more careful than operation of the whole canal. Hopefully this answered your question. Thank you.
Then also selected the time perform for I'll talk about it.
Okay. Yeah. Okay. Thank you. Thanks. Yeah. Just you feel free to finish the presentation and your questions are done. And thanks a lot. And have a good afternoon, everyone.
Bye-bye.